Uh, so, Hi, I'm Shota Elkanishvili, and today we will talk about how to trick a neural network. So, first of all, I will introduce myself. I'm a machine learning engineer at Teneo. At Teneo, we generate Stripe-like API documentations in few clicks. Teneo is backed by Y Combinatoric, and as it was said, we have just one Web Summit. And what I actually do at this company is I try to build AI assistant to automate API docs, like generating descriptions and just text, at this moment from text, but future from the code repositories. So let's dive into our topic today. So first of all, before I actually start talking about how to trick a neural network, we should ask a question. What are neural networks in general? Are they magic? So, as we know, most of the people know about neural networks, but they know it as a black box, that it has some kind of input, then some computation, some black box happens in between, and you actually have output. But what it actually is, they are simply functions, they are math, as it's right. So, it actually takes input, does some calculations, which are maybe linear functions, nonlinear functions, but finally, it's still a function, maybe combinations of many functions, but finally, it's a function. There are many tasks that neural networks can solve, and output describes different outputs are different for tasks. For example, if you want to predict house prices, you will predict one continuous integer or float, maybe. But if you're trying to see if this picture is dog or cookie, it will be distribution of probability. So probability would sum up to 1, and you will just say probability of this picture being panda is 10%, being cookie is 40%, and etc. So in this talk, we will mostly talk about image classification, but it's just one possible task we can use to trick neural networks. But yeah, that's it. And trust me, image classification is not an easy problem because, as you see, it's really hard to differentiate them. Okay, so our topic is about how to do adversarial attacks on neural networks. So this is fancy words, but what it actually is, we try to come up with inputs, to take original inputs, transform it, so that for humans it will be the same thing. We will still say that, okay, it's a panda, but for neural networks, they will be confused and they will think that maybe it's a paper towel or something like this. So how do we do it? But let's think why it should be so. Why can we do something that will be unchanged for humans, but it will be changed for neural networks? First problem in this logic is that neural networks does not think the same way we do. So our conscious system works differently. We see pictures in a whole, but every pixel matters, as we also see at the end of the talk, that every pixel matters. And we cannot describe how actually it works and why it decided. It has, of course, its mathematical terms, but we cannot verbally say why neural network decided that this is a dog and this is a cookie. So why should we care about adversarial attacks? Because in typical data pipeline, we have test data, which is something that we evaluate our models on. So we will say that, okay, our model will perform this way when it goes to production. But reality is we do not know how close this data is to the real distribution which happens in real world, right? And we, as I also already mentioned, that we do not know how neural networks work, think. Neural network does not know people too. What I mean by that is that people can do many, many weird things. I think when you first production your model, you'll find out that people can just make weird requests and make your model look silly. And with this kind of attacks, we'll try to come up with better training process That if you find out that, okay, if we go and if our model was tricked that way, it means that it can really decrease the performance of our product. So that will help us. So adversarial attacks really matters, and fuzzing is the same kind of thing in software world. If you're familiar with it, it's low-level way of attacking with adversarial examples. So motivation behind this talk. So I was reading book by Chip Huen, Designing Machine Learning Systems, and it was this first and third papers were mentioned. And when I actually read the papers, I realized that it really mattered. It was really interesting to find out how you can trick neural networks. Also, it helped me to understand how it really worked even better. So I will aim that you will also have better understanding of neural networks after this talk. And yeah, reading machine learning academic papers really help you to keep up to date with the industry. So let's stick with the classification task. What it really means to be classified. What it means that we say that this picture, neural networks say that this picture is pandas. So if you look at the chart down below, we will see that, so imagine this is a distribution of probability of being panda. So this chart is being panda. So X and Y plane is just population of images, and Z is how likely it is to be panda. And if it's high, it means that it's more likely to be panda, and if it's down, it means that it's not a panda. So with adversarial attacks, we will try to choose one class, for example, panda, and we will try to decrease the probability of this picture classified as panda and increase some other class. This attack will be targeted if we also choose another class, but if we say that, okay, we do not care about another class, we just want to declassify the concrete class and say that it could be anything else. So how should we do it? So we want to decrease the probability. And there comes another question. What is the fastest way down there? And it's gradient derivative and gradient descent, which is almost 90% of machine learning is built on this technique, which gives you the fastest way down. So we will use this one. So before we actually start thinking about this is the result. Came from original paper, and I do not really know what nematode is, but this was used in original paper, so I also used it. So we took first original picture, which is panda, and model is VGG, which is one of the first accomplished convolutional neural network, which came from Google, if I'm not mistaken, and it has almost 60% confidence that it's really pandas. So then we added some noise. For us, it's just random noise, but let's say that it's just noise. And after that addition, for humans, it is not just only still panda, but we cannot even differentiate what these first and third pictures. So we cannot say what is the difference, but we know that we added some noise. So our aim in adversarial attack is to find this concrete noise. So we will add this, and our model will be tricked. And again, this happened because every pixel matters. It is huge computations where, for example, these concrete numbers added so that after it was multiplied, then divided, added, increased, decreased, it was almost 100 confidence that it was given, which is so unfamiliar for us humans. And you cannot say that, you cannot predict that your model would have this kind of behavior. So that's why it matters. So let's start with black image. And then try to predict what are the possible labels, what are the possible classes for this. And as it turns out, model thinks that it's 27% velvet, 6% shower curtain, and I just chose paper towel, which gives us almost 5%. So I thought, why could we just still make it black picture, But let's say model thinks that it's a paper towel. What I did for it. So if you are familiar with transfer learning in machine learning, it's something like this. So you have already pre-trained model with weights, and you just retrain it on another data. So these weights are recalculated. So imagine same thing, but with additional layer as a picture. So imagine that picture. So input is also weights. So it could be gradient could be calculated, and it could be changed. And you are trying to optimize the neural network so that it will think that it's a paper towel. So if you look at that problem that way, what we can do is to calculate why, what was the feedback, why our model thought that paper towel worst 5%. And when you calculate gradient, it looks like this. It's almost nothing for us, but then idea came. What happens if we add this gradient? So what happens if we take in mind this whole process and see what happens? So after just one iteration of adding it by with coefficient of 0.9, it had 11% growth. And it's logical because we try to optimize our picture so that already trained model thinks that it's a paper towel. It's okay. So, but as you see, velvet has already also increased. But that's okay. And then natural idea came. Why should we just add it one time? Why can't we just iterate over it and actually do gradient descent on the picture? And when you do it, after fifth iteration, paper towel confidence increase and velvet confidence decrease. And yeah, so what can we say by now? So we can transform any picture to another class with some kind of step and after some number of steps. But thing is, we are not sure if it will be still or recognizable by human with the same class. Because gradient works. You can always transfer something to another thing. But the thing is, if you can still keep the structure, so humans will still think that it's a panda. So another algorithm I will talk about today is one pixel attacks. And as you see on the from left side from you, is that by changing only one pixel, the model thought that it was another thing. It thought the deer was airplane with 85% confidence. So it means that something is wrong where we approach the whole training process. This data came from CIFAR-10. It's famous toy data set for machine learning practitioners. And yeah, so we have new mission to try to change only one pixel so that it will be misclassified. Okay, how can we do it? So first idea is to create a random pixel generator. So randomize position of the pixel and random the actual RGB values and hope that it will be misclassified. But there is no guarantee that it will, if it converges, right? Because there is no guarantees when you are doing random search. But then when search space is so huge and you want to go with one kind of direction, the best algorithm, and from my point of view, one of the most beautiful algorithm is genetic, aka evolutionary algorithm. So as you heard, it's called genetic, and it really is connected to evolution and genetic in general. So what we do, we have some concepts like genes, DNAs, and populations. So imagine genes like some states or some features which describe the individual. For example, in our case, we can save transformed picture with one pixel. Or we can just have 5 values, x coordinate, y coordinate, r, g, and b values. So these are the genes how we describes the individual. Then there is a DNA. DNA is list of genes, and population is list of individuals. And this is how the process goes. So it was different visual, but it's okay. So we just randomize whole population. So we randomize these concrete genes, these 5 values, and yeah, for example, we have 100 individuals. Then we do a thing called fitness test. Fitness test is something how we measure how our individual worked. In real life, it could be just life, who just left alive and reproduce or something like this. So in this case, what we can do is to just go through the network, first change the original picture and try and see the confidence, how confident it is it's still same thing. Then we will choose the best candidates, and in our case, best candidates will be the ones who had the lowest probability of labeling that data as panda. And then we do mating, reproduction. So we choose 2 candidates and do some mathematical operations. So we create a new individual with this. So it could be just average of those 2 numbers. It could be just weighted average with their confidence, or any other mathematical expressions that make sense in this case. Or we can also do mutation, because there is a chance that in the first population, really good genes did not came up. So we will, with some percentage, we will do mutation, and mutation will be just forgetting about the parents and re-randoming it again. So this is how it works. And yeah, it's not always possible for every model, because yes, every pixel matters, but not always. You cannot always change one pixel and say, let the model think that it's something different, because today's models are really, really good at something, but at some amount of pixels, it will be available. So there are 3 pixel attacks, 5 pixel attacks, the same algorithm, but different number. Yeah. And why? What can we learn from these adversarial attacks, and how can we, and the thing to trick neural networks? What we can learn is there is really something fundamental thing missing in the training process, because this kind of thing should not be happening. But maybe problem is that we think that neural networks should also think the same way we think. And if we think that it's not okay to predict this incorrectly is not the case. But what we also can do is to do it ourselves, do adversarial attacks, and I did it myself, and I really enjoyed the process, because implementation of this algorithm is really meaningful and gives you something, and also learns you many things, teaches you many things. And with this kind of examples, you can just know how your model will work before productioning it, and you'll be able to enrich your data. You can do some kind of data augmentation with this kind of things, and let your model learn that these kind of things can happen, and learn this too. So that's it. And if you have any kind of questions, please.
Shota, first of all, thank you for great presentation, and also solving finally Malebich square puzzle. Let me ask you a question.
Sure.
Regarding this reasoning mechanism. We do not know even how human being is generating thoughts and what is behind that. But we have some approximations. Yeah? We're getting more and more insights, and we can replicate, and we can endow neural networks with these capabilities. And how do you think, what is key capability of human reasoning which enables our mentality to avoid deception? So everything is about avoiding deception, right? Preventing deception.
Yeah. So I think short answer would be evolution, that human mind and human cell is developing and evaluating for how many years. And we just started and we are trying to mimic how we think. For example, self-supervised learnings are the keys that we try to, let's say, model solve the task we think we are solving when we are doing something. Like, for example, inverse reinforcement learning, when you give the examples and you give them to learn it. So I have thought about this, but I think it just it evolves that way. It is so complicated. As, for example, protein folding example. The search space is so huge. It's unbelievable how one cell is capable of that kind of search, that it can find the correct folding of the protein, right? And it's unbelievable how can it do it, how can it compute or what algorithm is behind that. And I think it's just pure magic how we evolved. Magic, I mean pure interesting thing how we evolved and how our brain optimized all these things. And I think main thing why we are not up to date with this is that we are just starting. And I think after some time we will reach that point, I guess. I'm not sure how good this answer is, but that's what I think about all of this.
Thank you, Shota, again. As I understood, the adversarial attacks are some kind of data augmentation mechanism. And I want to ask if you have done some research in other classification tasks for neural networks, for example, text classification, and how the adversarial attacks can be used for tasks.
Yeah, thank you for the question. So, thing is, I think these concrete algorithms are not dependent on task like vision, right? Because it's just the idea of first algorithm is to try to do gradient descent on input, and another one is to do genetic algorithm. So thing is, the hardest problem for example text is if you go through derivatives and gradients, you cannot actually change text, right? So text is something that it makes sense or not make sense, and then you want to go into the embedding layer, right? But most of the time you're not allowed to access the embedding layer as a user sending input, right? So for text, I do not think it is possible to trick it with the first way, but with second option is also possible. I have not done it, but I guess it's possible because you will just try to just for example replace one character, and try to find the way with genetic algorithm to find the sentence which will confuse our models. Other things which is represented as numbers in the first place and not, for example, strings. Like both of the algorithms could be happening. But with text, text is so concrete. Also, maybe speech will be the same. But yeah, it depends on what layer you are trying to attack. If you are trying to attack the pure layer, it's different. But if you can access the embedding layer, you can do whatever you want because it's numbers, right? So that would be my answer.